In this video, we will explore the benefits of quantitative over qualitative statements in science and in daily life. Math. The word alone probably has some of you in a cold sweat. Why is that? I suspect it has to do with the exact nature of mathematics. In math, 2 plus 2 equals 4. If you come up with any other answer, it would be marked wrong. Your personal opinion is irrelevant. Math is the exact language of science, and numbers are the alphabet of mathematics. Why do science, medicine, and engineering rely so heavily on mathematics? Suppose you get the results of an exam. Someone asks you how you did on the exam. You say, "I did well on the exam." This tells the other person you are pleased with your result. The problem is that what one person may consider doing well on an exam may to another person be unacceptable. Had another person received the same score, they may have said they were disappointed by their score on the exam. When you say you did well on an exam, you're issuing a qualitative statement. Qualitative statements are more like inferences or opinions. What we want in science and medicine is to bring inferential statements down to the descriptive level. We do this by translating the qualitative statement into a quantitative one. You could say, "I scored 85% on the exam." Most students would probably consider 85% a good score, but not those who were expecting an A. Suppose you take a friend to the ballpark. Your friend says, "Wow, the ballpark is really crowded." Your friend's statement is a qualitative statement, an opinion. You may not consider the ballpark to be crowded at all. You may be used to going to the ballpark. Your friend may be from a small town. If there were 15,000 people in the ballpark, that may be more people than live in your friend's town. We can turn your friend's qualitative statement into a quantitative statement by waiting for the public address announcer to give the official attendance during the 7th inning. Or we could say the stadium is about 3/4 full. You make the qualitative statement, "Regina is tall." However, whether Regina is considered tall will vary from one person to another. For people shorter than Regina, she most likely will be seen as tall. But for people taller than Regina, she may be considered short. If Regina is 5 foot 10 inches, she is taller than the average adult female. But if she were a college basketball player, she may still be considered short for the sport she plays. So to translate "Regina is tall" from a qualitative statement into a quantitative statement, we can say Regina is 5 foot 10. The context will determine whether we consider Regina to be tall. Let's say we have 2 water baths. One is at 40 degrees Fahrenheit, and the other is at 80 degrees Fahrenheit. Into each bath we will place one of our hands. We leave them there for a few moments, and then we move our hands to a bath of intermediate temperature, say 60 degrees Fahrenheit. What will our hands tell us? One hand will say, "The intermediate bath is warm," whereas the other hand will say the intermediate bath is cool. Which is correct? Which one is telling the truth? In reality, both are telling the truth because What they're reporting are the changes from prior conditions. The hand that was in the cooler bath will report the middle bath as being warm. The hand that was in the warmer bath will detect the middle bath as cool. Do you see the ambiguity? If these were two different people with their hands in the middle bath, and one says it's warm and the other says it's cool, we could end up in an altercation. On the other hand, if we put a thermometer in the middle bath and measure the temperature at 60 degrees Fahrenheit, we can both observe and agree on that. Using a thermometer, we translated the qualitative statements, "it's warm" and "it's cool," into a quantitative statement, "it's 60 degrees Fahrenheit." I hope you are beginning to see the importance of translating qualitative statements into quantitative ones in order to move from what amounts to the inferential level to the descriptive level. Remember, in science and medicine, we want to minimize ambiguity, and so we value the descriptive level more than the inferential level. There are three methods we can use to translate from the qualitative to the quantitative. We can estimate, we can count, and we can measure. Let's look at examples of each. Here's an example of counting. Let's say you go to the store and buy some items and the cashier tells you that you owe $9.47. You can't just hand the cashier the change in your pocket and walk away. No, they need an exact amount. They want $9.47. So you have to count out exactly $9.47. Counting is a way of determining exactly how much. Another way of translating a quality into a quantity is to measure. Here is a line, and we want to know the length of the line. So we get a ruler. We place the ruler next to the line, and then we count the marks on the ruler so that we can determine the exact length of the line. There are many qualities that we can measure and translate into quantities. We just measure the length of a line with the assistance of a ruler. We can measure our mass or weight by stepping on our bathroom scales. We can measure volume of coffee in our cup by pouring it into a measuring cup. We can measure the sweetness of our beverage by measuring the concentration of its sugar content. We can measure the pressure of the atmosphere by using a barometer. We can measure our oral temperature by using a thermometer. We can measure the sourness of a solution using a pH meter. We can measure learning using an exam. The exam is an instrument for translating the quality of what we know into a quantity like 95% or 78% that can be used to objectively evaluate and compare students. In the meantime, a student can decide whether their score is good or bad. Another way we can translate the qualitative into the quantitative is by estimating. Sometimes there's just too many things to count, and we don't have enough time to count them. Or there is no instrument available that allows us to do a measurement. There are principles of estimation we can use that can help us obtain a more accurate estimate. A few years ago, I was doing a science Olympiad where students had to estimate the number of beads in a jar. There were too many beads for them to count, so they had to use a principle of estimation. If the students just pulled a number out of thin air, they would likely be a long way off. If they used a principle of estimation, they should be able to get much closer to the actual value. That's what I was looking for. If a student counted the number of beads in one layer of the jar and the number of beads in a column and multiplied them together, they could get a pretty close estimate of how many beads would be in the jar. Those students who thought of this principle would be more likely to get closer to the number of beads in the jar than those who simply guessed. If you're at a ballpark and someone asks you to estimate the attendance, you can look around and then pull a number out of your hat. But if you use a principle of estimation, you will more likely be nearer to the actual attendance. If you know the capacity of the ballpark, say 40,000, and observe that the stadium appears to be only half full, you can conclude there are approximately 20,000 in attendance. There would be no way for a person in the stands to count that many, and pulling a number out of thin air is not likely to get you anywhere close to the actual number. But applying a principle of estimation, like the one mentioned, should permit a credible estimate of the attendance.